thing we are going to apply for a different plane, that's all. So the three components are going to be the same, delta Fz, delta Fy, delta Fx, the same three components. Now the plane direction alone is changing to this kind of plane, that's all. So these three components we are applying for this plane, that plane which is perpendicular to y-axis. So this is correct only. So first I am applying the force which is acting on Z along delta A, and in this case it is going to be tau. So when this is going to be normal, only if it is applying on y-axis, yes, y-axis. So it is normal. So only at that place I will put sigma. In all other places I can write only the tensile tau. So tau of yz is nothing but Z component of force acting on delta A, and I of y-axis, the x component is acting on delta A, both are tensile stress. And when y component is acting on the direction, on the plane perpendicular to y-axis, it is the normal stress, so it is sigma yy. So this is nothing but this plane. This plane, that is the one which is perpendicular to y-axis, right? So this is the normal component, which is the normal component of stress, and these two are the tangential components of stress. So tau yz, tau yx, right? So these are the next three components which can be explained in different directions, acting, the stress acting in different directions. And tau yz, sigma yy, tau yz, I explained from here itself. Similarly, you do it for the x-axis, a plane normal to x-axis. You apply all the three components of force. Z component of force, when you apply, it is going to be in this portion, right? The plane normal to x-axis means it is this plane. Only when x component of the force is acting, it is going to be the normal stress. Other two stress values will be tangential, so I prefer to write tau. So when Z component of force is acting, when Z component is acting on a plane perpendicular to x-axis, it is the tau xz, and the next one is a tau xy, and the normal component is sigma xx. So we require all the 9 components to explain the total stress experienced by the point P, right? So this plane and the drawing alone is shown here separately. When you write the stress tensor, you have to write all the components like this. This is the stress tensor which is in the matrix form. Sigma ij is equal to sigma xx, tau xy, tau xz. This is what we have seen in the previous slide, right? All these three are shown here, sigma xx, tau xy, tau xz, and in the previous slides whatever we have seen, those components are consolidated in the matrix form. You see, in normal, without using tensor, if you are measuring the stress, you just get the information about what value of the stress, the magnitude of the stress alone you will be getting. Now if you are writing it in the form of a tensor, you are elaborating the information in every direction. What is the magnitude of the stress that point experiences in these two directions? So that particular physical quantity, the stress, right, it has the magnitude with reference to the two directions. The first direction, it represents the plane which experiences that force, and the other one represents the direction of the force itself. So earlier when I defined the dyadics, you might be wondering how a physical entity can have a magnitude under two directions. Now you can understand, even though it is a particular quantity called the stress, you see how much elaborated information you are getting. Instead of getting only the magnitude, now you are getting its magnitude that is described in terms of two different directions. In whichever direction, in whichever plane you want the exact stress magnitude, the point experienced, you will get it, right? That is the beauty of tensor. It can elaborate the information with respect to the directions. So every component, it gives you the magnitude, and each subscript, the first subscript here, it represents the direction of the normal vector of the area, and the second subscript, it describes the direction of the force. So such elaborated information